Module 2.2. As a reminder, it's recommended to print the video script and annotate the script while watching the video for later use. Video scripts are available on Canvas. Module 2.2. How can researchers study the relationship between variables? It is often the case that we would like to know about the relationship between two variables. You've probably read about studies involving two variables without realizing it. Visit the health section of any major news outlet and you'll find an article like this one. Take a moment and read the article. The news article is looking at the relationship between the following two variables: type of marijuana laws and number of opioid prescriptions. To determine if the two variables are related to one another, we must first determine how the two variables may be interacting with one another. We usually identify one of the variables as the explanatory and one as the response. Definition. The explanatory variable is the variable which will help us understand values of another variable. It is also known as the independent variable. In the news article, where a state has marijuana laws would be the explanatory variable, since the researchers are looking to see if marijuana legalization can change opioid prescription patterns. The response variable is the variable we want to observe change in based on the explanatory variable. It's also known as the dependent variable. In the news article, the number of opioid prescription patterns would be the response variable, since the researchers are looking to see if the number of prescriptions changes based on whether a state has marijuana laws. Your turn. Pause the video and read the following examples, and identify the explanatory and response variable. Suppose we are interested in determining if a person's BMI explains the time they sleep each night in minutes. In this case, BMI is the explanatory and time slept is the response. Researchers want to know if owning a dog reduces a person's stress level. In this case, the explanatory would be whether or not a person owns a dog, and the response would be the stress level. A professor would like to know if a student's GPA can be explained by the level of homesickness a student experiences. Here, the explanatory would be the level of homesickness, and the response would be GPA. What kind of relationships are possible? There are two kinds of relationships that we need to distinguish. Definitions. Two variables are associated if the values of one variable exhibit a pattern with the values of another variable. Associations are visual. We can see associations by looking at a plot or comparing numeric summaries. Associations do not necessarily mean that one variable has a direct influence on the other. Causation occurs when one variable directly influences another variable. The distinction between association and causation can be tricky. The key is to remember that associations are only visual. Understanding the distinction can be hard for people because when we see visual patterns, we tend to think that there is some underlying cause for the patterns. When looking at plots, many people are tempted to conclude that two variables are linked since there is a pattern, and it's not obvious that there is no causation. This is not the case. Remember that associations do not determine causation. This brings us to an important rule. No matter how clear the pattern between two variables is on a plot, we never use a plot alone to determine causation. We'll begin by looking at an example where there is a clear visual relationship but no causation. Suppose a scientist recently saw the Snickers commercial featuring the sharks who love Snickers and becomes concerned that people who eat Snickers ice cream are more prone to shark attacks. If you've not seen the commercial, there's a link in the video script for you to watch. The scientist has little funding and cannot perform a proper experiment, so he gathers data on the number of boxes of Snickers ice cream sold and the number of shark attacks in the same coastal region as the sales. Creates the following time plot. First, it should be noted that this is a terrible graph. Later in the course we'll learn techniques to make easy-read informative plots. Let's start by identifying the explanatory and response variable for this example. Notice in this case, the researcher wants to use ice cream to explain shark attacks. So for this reason, the explanatory variable is ice cream sales, and the response variable will be the number of shark attacks. Next, by looking at the plot, notice that ice cream sales and the number of shark attacks exhibit a similar pattern over time. This is an example of an association. The variables ice cream sales and number of shark attacks are associated because over time we can see they exhibit a similar pattern. Later we will look at different types of associations. What we are interested in learning is, do ice cream sales cause shark attacks? The obvious answer here is no. Realistically, we know that ice cream sales do not cause shark attacks. It turns out that many variables will exhibit patterns over time, but there is no causation. Sometimes it's easy to determine there's no causation. Consider this plot. This plot is making a comparison between the number of films Nicolas Cage has appeared in and the number of people who have drowned in a swimming pool. Notice that these two variables have a similar pattern over time. Thinking rationally, we can see that it's obvious that the number of films Nicolas Cage appears in has nothing to do with the number of drownings. Other times, it's much harder to determine there's no causation. Consider the following plot. This plot is making a comparison between the number of individuals diagnosed with autism and the sale of organic foods. Notice again that the variables have a similar pattern. In this case, it is not obvious that causation is not present. Why do some variables exhibit an association when no causation is present? Definition. When confounding is present, we cannot determine if the change in the response variable is due to the explanatory variable or a third variable. One way that confounding may occur is when a third variable that is not accounted for in the study and associated with both the explanatory and response variable is present. These variables are called confounding variables. Alternatively, confounding occurs when a study is flawed and the effects of multiple explanatory variables cannot be separated from one another. Confounding may explain why we see a pattern between the explanatory and response variables even when there is no causation present. Whenever confounding is present or may be present, we cannot conclude that there is a causal link between the variables. One way to think of the relationship between these types of variables is to think of a system of gears where each gear represents one of the variables we have discussed. Suppose that we have a gear representing the explanatory variable and a gear representing the response. We want to see if when the explanatory variable is turned, it is responsible for the response variable turning. Notice in this image, when the middle gear is turned, the explanatory variable and the response variable will also turn, even though the explanatory variable never touches the response. We would say that we have an association since both gears turn, but no causation since the gears do not touch. The third gear in the middle is the confounding variable. Notice that the confounding variable touches both the explanatory and the response. This is just one possible scenario. We could have more complex scenarios where both the explanatory and confounding variable touch the response variable gear. In either case, the explanatory gear is not solely responsible for the response gear turning. When the explanatory variable is causing a change in the response variable, there is no confounding variable present. Notice in the pictures here that the explanatory gear touches the response variable gear. Recall the shark attack example. The increase in ice cream sales does not cause the increase in shark attacks. Warmer temperatures cause increased ice cream sales and increase in shark attacks. So for this example, a confounding variable could be the weather. Another way for confounding to occur is when a study is flawed and the effects of multiple explanatory variables cannot be separated from one another. For example, suppose that you took a class where you performed poorly on the first exam. To prepare for the next exam, you visit the tutoring center, visit office hours for help, and work all the problems in the textbook. On the second exam, you score a 100. You want to know if visiting the tutoring center caused your exam score to increase. In this case, you do not know which of the three methods helped your second exam score. You cannot conclude that visiting the tutoring center caused your exam score to be higher. Your turn. Read the following relationships and identify a possible confounding variable. Pause the video, then come back and see some potential answers. The total number of salmon consumed and the total amount of asparagus consumed worldwide are closely related over the past 100 years. The confounding variable is world population size. Over the last 100 years, the number of people has increased and therefore the amount of salmon eaten has increased. Similarly, the amount of asparagus eaten has increased. People who own a private movie theater are more likely to buy a sports car. The confounding variable here is wealth. Wealthy people are more likely to buy sports cars. Similarly, they are more likely to own a private movie theater. People with shorter hair tend to be taller. The confounding variable is gender. Males tend to be taller and have short hair. Females tend to be shorter and have long hair. Now, one thing to notice here, we are talking about general trends. This is not to say that all males have short hair or all females have long hair. If plots cannot tell us about causation, how do researchers determine if there is a causal relationship? Whether or not causation can be established between two variables depends on how the data for a study was collected. Some studies are backward-looking, retrospective, or forward-looking, prospective. Definitions. When a researcher collects data by simply observing and does not influence the variable in any way, we call the study an observational study. Observational studies can be descriptive or comparative. We will look at three types of observational studies. Cohort studies. Groups with a particular characteristic are known as cohorts. A prospective study involving the comparison of cohorts is called a cohort study. Retrospective cohort studies can also be performed when trying to compare the risk of developing a disease to some already identified exposure factor. Located here and in the video script is a link for you to read more. Case control study. A case control study is a retrospective study where subjects with the outcomes of interest, case subjects, are compared to subjects without the outcome of interest, control subjects. Existing data for both the case subjects and control subjects are obtained to determine what factors related to a subject becoming a case or a control. Located here and in the video script is a link for you to read more. Cross-sectional study. In a cross-sectional study, data are collected at a particular time point and represent a cross-section of time. The outcome variable of interest are measured at the same time. In your group project for the course, you'll be looking at a cross-sectional study. When a researcher collects data by actively controlling the explanatory variable, we call this an experiment. To establish causation, the researcher must collect data through an experiment. The reason is that experiments can help prevent confounding, and this brings us to an important fact. Observational studies can almost never be used to establish causation. The invalid assumption that correlation implies causation is probably among the 2 or 3 most serious and common errors of human reasoning. Your turn. Read the following studies and determine if they describe an observational study or an experiment. Pause the video while you work on this and come back to see the answers. For the first one, a statistics student stood outside the UK library and watched students entering and leaving. She recorded whether the students entered as a group or individuals and kept track of the amount of time they spent in the library. She's interested in learning whether or not the students who go to the library as a group spend more time in the library than those who go alone. Notice this is an observational study because the student is only observing what people are doing without influencing whether they go to the library alone or in a group. A veterinarian would like to see if grain-free dog food is better for dogs. He examines the dog food without or with grain. He supplies 5 dog owners with grain-free food for 1 month and a different 5 dog owners with dog food with grain. After the month is over, the dogs come into the clinic and he measures different health markers. This is an experiment because the veterinarian is telling the dog owners what type of food to feed the dogs for the month during the study. How can experiments help us avoid confounding? Performing an experiment does not guarantee that confounding is not present. Careful setup and execution of an experiment can prevent the chances of confounding being present. The best way to prevent confounding is to assign values of the explanatory variable randomly. Definition. In a randomized experiment, the explanatory variable for each subject is assigned randomly before the response variable is measured. The different levels of a single explanatory variable are known as treatments. To set up a randomized experiment, we can randomly divide the subjects into groups and assign a different treatment to each group. Because the subjects are randomly assigned to treatments, the explanatory variable is not associated with any other variables, and confounding is eliminated. Suppose that we have the following people volunteer for a study. In the study, we would like to compare aspirin to Tylenol to see which drug alleviates headaches more quickly. Notice here that the two treatments are aspirin and Tylenol. Our first step is to assign each person to one of the two groups randomly. We can do this by assigning each person a number from 1 to 12 and using a random number generator to select 6 numbers to place in group 1. Suppose a random number generator tells me that subjects 1, 4, 5, 6, 9, and 10 should be in group 1. We would have the following groups. Group 1 would be the Tylenol group, and notice here we have the subjects corresponding to 1, 4, 5, 6, 9, and 10. And then the other subjects would automatically be placed into the aspirin groups. All of the subjects in group 1 will receive Tylenol, and all of the subjects in group 2 will receive aspirin. If a randomized experiment yields a significant difference between the two groups with respect to the response variable being studied, we can establish causation from the explanatory to the response variable. Located in the video script, and here is a link for you to follow to read more.